All right, hello and welcome everyone to our monthly Saga Talks. Welcome to all the Saga members and members from affiliated society and everyone who tuned in for the talk. Today's talk on magnetic resonance geophysical methods for groundwater investigations is kindly presented by Dave Walsh, who's joining us from Seattle, Washington. I hope the weather in Seattle right now is better than in Johannesburg, where it's quite overcast and rainy. Dave is a president of Vista Clara, and it's a business focused on developing manufacturing magnetic resonance geophysical instruments for groundwater and environmental investigations. Dave received his Bachelor of Science degree in electrical engineering from Iowa State University, his master's and PhD degrees in electrical engineering from University of Arizona. Dave has been the president of Vista Clara since 1997. His contributions to the field include development and commercialization of the world's first multi-channel surface NMR instrument and development and commercialization of the world's first small diameter NMR borehole logging tools. Dave, I'm going to share your presentation. Just give me 1 second. And I'm going to share your video, and the floor is yours.
Okay, can you hear me all right?
Yep, read you loud and clear.
All right, well, thank you. Thank you for the opportunity to present this today. I'm going to kind of keep the presentation on a scientific level. First of all, what is magnetic resonance? It's a good question. It's a non-invasive method to directly detect hydrogen. And it's also applicable to a few other types of elements, but hydrogen is the main one that we're concerned with in groundwater and in geophysics. So a hydrogen atom, let me switch to the, let's see, I'm trying to get the pointer, laser pointer, here we go. So a hydrogen atom, basically it's got a single charge on it, a positive charge, and the proton, and it's spinning, and so therefore it acts kind of like a current loop, and it therefore has sort of a dipole magnetic moment. So a lot of elements do not have this property. Hydrogen is one that does. So what we're basically doing with magnetic resonance is we're detecting the very small magnetic moment of the hydrogen proton. And it's such a small moment that you can't detect it if there's only one. You have to have a very large number of protons to have any hope of detecting it. But, you know, billions and trillions of hydrogen atoms can certainly give you enough of a moment to detect. So the other thing about magnetic resonance is that it's a sort of a resonant phenomenon. And so the way you detect it is actually by causing an excitation at a particular frequency at which the proton will respond to an external magnetic field. And we'll describe that in a couple of slides. But that's basically it. It's non-invasive. You don't have to touch it. Doesn't have to be contact to detect the hydrogen. And another key point is it is not a radioactive technique. It doesn't require a radioactive source. And that's a common misconception about nuclear magnetic resonance, because it's got the word nuclear in it. So sometimes we don't even use the word nuclear. Oh, that's the scientifically more accepted term, nuclear magnetic resonance, NMR. So let's see, where is magnetic resonance used? Originally, it was developed in chemistry in the 1940s, and it's used widely in organic chemistry and pharmaceutical industries and all sorts of applications, basically to map out and understand chemical bonds at a molecular level. And I won't get into it here, but if you had a course in organic chemistry, you may recall this. So you have individual bonds in a particular molecule can cause very slight shifts in the resonant frequency, and with a powerful enough magnet and machine, you can resolve these different frequency shifts and use them to identify exactly what the compound consists of. Another very widely used application of magnetic resonance is in medicine, with medical MRI. In this case, you have a machine that you put a person inside of it, and the objective is to image the body so that you can diagnose disease and injury. And a third widely used is in oil and gas, in borehole logging. And so that's one of the things we're doing in groundwater. So it's not new. It's just a different field of application to the oil and gas sector. So how does it work specifically? Well, first of all, you have to have hydrogen protons. And the magnetic moments of a hydrogen proton in general, if in the absence of any sort of external field, will just be randomly oriented. And therefore, the bulk quantity of volume of water or whatever fluid you're trying to detect will not have any magnetic moment. So the first thing you need to do a magnetic resonance measurement is a static magnetic field. In this case, we're using a icon of just a bar magnet to sort of give an idea of how this works. So if you have a static magnetic field, just like compass needles tend to align in the direction of the North Pole, same thing happens with the hydrogen atoms. So you use a static magnetic field to orient and polarize the water magnetically. So the second thing is to get them to rotate. So the second step is at one particular frequency, which is directly proportional to the strength of the static field, you have a resonance. That means that the water will respond, the hydrogen atoms will respond to an external magnetic field, an alternating magnetic field at that frequency. And they respond by spinning around in phase. So it's kind of like if you had a magnet and you were driving it with some sort of a magnet, kind of like the way an electric motor works. You're driving it with an induction coil, and that causes the magnets to physically move in phase with that external field. So the hydrogen atoms are rotating around in phase at a particular frequency after the excitation process. And then the third step is to detect. And so basically to detect, you just turn off your exciting field, and these protons will continue to, for some period of time, rotate in phase, and that generates a secondary alternating magnetic field that's detected, typically by using another induction coil. All right, so that's kind of the most difficult part of this talk, just trying to get the basics and trying to understand them. So how does this relate? How does an NMR signal relate to a hydrology then? So here on the left, let's say we've got this earth material of some sort. Maybe there's sediments there, but there's water in between, in the pore spaces. So the first thing is that the total water content in the volume of investigation, that is whatever the particular sensor is sensitive to, the total water content is the NMR signal amplitude is directly and linearly proportional to the total water content. So it's a direct measurement of water content, volumetric water content. And if the medium is fully saturated, then it is a direct measurement of porosity. So that's very interesting on its own, very useful. So the second thing about the NMR signals, it's got an initial amplitude, but then it also decays over time. It doesn't continue to rotate, these spins don't continue to rotate forever after you've excited them. So it turns out the thing that governs that relaxation rate, as we call it, or the decay rate of the detected NMR signal, is usually interactions between individual water molecules and pore and grain surfaces inside the material. So basically, if you've got water that's in a large pore, these interactions don't happen as regularly, and therefore you can have a long signal. The NMR signal tends to have a long relaxation time for water in large pores and a fast relaxation time, a short relaxation time for water that's in small pores. So that's how NMR can be used to differentiate between water that is mobile, let's say in sands and gravels or large fractures, versus water that is immobile. That is, it's in very small pores that are water's bound by capillary forces or else in clay. So this is basically, if you've got your geologic material like we have here, you've got a combination of large and small pores. There's no natural material that's going to have all the same size pore. You generally have a distribution. So the NMR signal is going to be a super linear combination of all of these signals, small and short. So you have typically an NMR signal will have a multi-exponential decay rate that reflects the pore size distribution, or at least the relative pore size distribution. So water that's in really small pores, like this little space here, is going to have a faster relaxation time, and water in these bigger pores, larger geometries, will contribute a signal that lasts for a longer period of time. And so just by integrating different parts of this curve, so basically here's your model, and you can convert your model is basically a relative pore size distribution here. So you can characterize all of the water that's in the short pores, the small pores, as being bound just by applying a cutoff in this time domain distribution. And so this isn't a direct measurement of bound and mobile water. It's an estimate, but it's based on empirical and understanding of where those cutoffs happen in different types of material. Finally, you can use this pore size distribution and some other derivative, NMR measured derivative, such as the amplitude, the porosity, or the mean log of the T2 relaxation to estimate permeability. So this is one step further from a direct measurement. It is just an estimate. It's based on some sort of an empirical model. That's the relation between the NMR signal and hydrology. How do we infer hydrogeological properties from the NMR signal? Now, there are different types of instrumentation that use NMR in geophysics, and basically they're all doing the same type of measurement. They're all doing an NMR measurement in the cases that we're usually working in, trying to determine hydrogeological properties in native earth formation material. But these different methods, they look a lot different because they're basically using different magnet geometries and different types of detection, different types of instrumentation that have different sensitivities. So for example, surface magnetic resonance, you're using the Earth's magnetic field as the static field. And so this is completely non-invasive. You have a big loop of wire that sits on the ground, and you're generating your excitation fields from that loop of wire and generally detecting the signal using the same wire. Borehole NMR logging is much different. In this case, you've got magnets in the probe in the tool that's going down the borehole, and they're creating a sensitive zone that's hopefully outside of the disturbed zone and in the native formation surrounding the borehole. And there's some other types of instruments that are more specialty, core sampling and near surface soil measurements. So we'll start with the borehole logging. So basically, this is a borehole logging tool, small diameter tool, and this is sort of a representation of where the sensitive zones are. So this tool has magnets, permanent magnets in the sensor, and it also has induction coils in the sensor in the same vicinity of the magnets. And so the magnets cause the polarization of the hydrogen atoms in these native formations surrounding the tool. And the induction coils perform the excitation and detection function. one thing interesting about the borehole logging tools, most tools are used in groundwater have this sort of design where you've got these sensitive zones that are thin cylinders that surround the middle of the tool. And the reason these sensitive zones are cylindrical is because the magnets in the center cause a field that varies radially as you go away from the center of the tool. So the static magnetic field is decreasing as you move out. And therefore, the resonant frequency at which you can do the NMR signal is also decreasing as you move from here out, radially out. So by selecting a particular frequency at which to do your NMR measurement, you are effectively selecting a particular measurement zone. So some tools have multiple measurement zones, and the way you achieve those is simply by tuning the coil differently and doing measurements at different frequencies. So you basically get multiple shells that extend at different depths of investigation. The other thing about this, it's really important to understand is that you're gonna with a logging tool like this, you're gonna only be measuring water right on that cylinder, in that cylinder. It's a very thin, typically only 1 or 2 millimeters is typical. So it's a very well-defined geometry where you're actually doing your detection. And the key thing is you want that shell to be in the native formation, not in the disturbed zone. If it's in the disturbed zone or if it's in some combination, the NMR measurement is going to report whatever is in that shell. So one other thing is NMR logging cannot be used in metal casing. That's because it operates at high frequency, typically hundreds of kilohertz. And a metal casing will shield those fields and not allow the alternating fields to escape into the formation. Okay, so here's an example of how data go from an NMR logging tool and a data set are processed and interpreted. So on the left here, you basically have, at each depth, you've got a different measured NMR decay curve. And these are shown just on a color scale here. So you see where there's longer signals like here and shorter signals in here. So this is the actual measured data here as a function of depth. And the next window here is the T2 distribution. That's the time decay distribution, which you can also consider to be a relative pore size distribution. So here where you see the longer lasting NMR signals, you see more water showing up in these larger relative pore sizes. And then by taking a cutoff, applying cutoffs on the time decay distribution and integrating, then you have your total water content here, which is the entire curve. And you can segment and estimate fractions of clay-bound, capillary, and mobile water content. These are, again, just estimated based on cutoffs that are hopefully, based on something that's known properties for the particular material. And then your hydraulic conductivity, again, comes from a model relating the NMR measured property, the NMR measured parameters to the hydraulic conductivity, and transmissivity is finally just the integral of the hydraulic conductivity. So I'm going to show a few interesting, I hope, examples here of NMR logging. The first one is in groundwater resources investigation. This is the city of Denver, Colorado, and they have long-term water issues to support their growth in that area. But they have some very productive and permeable aquifers beneath the city. So what they're trying to assess is whether they can take water some years they may have excess water available to them in the South Platte River. That is, there's more water than normal because of larger than normal runoff due to snowpack or whatnot. So they would like to be able to take that water from the river and inject it into these aquifers beneath the city just to store it for later use. These aquifers are deep And generally they kind of slope down from the Rocky Mountains foothills here, and then kind of like a bowl-shaped geometry underneath the center of the city. So the trouble is they don't have very much information on where these aquifers are and what their properties are beneath the city of Denver, because it's highly developed in that area, and it's not easy to find. There's not a lot of new wells going in that they can use. So a few years ago, they decided to do some exploration drilling to try to characterize these aquifers. And they specifically wanted to use geophysics and specifically NMR logging to characterize these aquifers. So these wells were drilled in 7 different areas where they didn't have much information. The drill cuttings as they were coming up were quite concerning to the hydrologists who were running the project because they really weren't indicating aquifer materials. It was kind of a big combination of broken up shale and clay, and it wasn't until they did started doing the NMR logging in particular that they started to breathe easier, and they said, okay, there are aquifers down here. So here's a couple of NMR logs from 2 wells that are not very far apart, and so this is the sort of data that you get from an NMR log. These are we're just showing here is the mobile water content. Things are really interested in this application where what's the mobile water content, which is basically the effective porosity, how much water can be stored and moved. And second, and probably most important, is the permeability. But you see, these aquifers, their characteristics, both in terms of their hydrogeologic properties and their depths, they vary quite a bit, or even over a few kilometers here. So this is exactly the sort of information they were looking for. For example, this upper Arapahoe aquifer, a little bit off to the west at 40th in Colorado, it's a much more productive aquifer with higher permeability and bigger sections of good aquifer material than it is just 3 kilometers or 4 kilometers to the east. And then the lower Arapahoe, it's the opposite. Over to the east, it's much more better aquifer in terms of storage potential and recovery than it is a few miles off to the left, east. So these measurements were, I think, very cost effective considering the cost of just drilling these wells was about $200,000 a well. And these wells were immediately abandoned. They were just drilled only for the purpose of getting the geophysical data. All right, a couple of quick examples, I hope, on the geotechnical application. This example, this was in London, UK. They were drilling boreholes to characterize sediments underneath the Thames River for the purpose of planning to build tunnel, at least 1 tunnel, maybe 2. And so this kind of gives you the sort of the idea of the information that you can get. These are the permeable zones, mostly sands, although it's quite mixed, interbedded, more consistent clay in this zone. Again, sand, a little bit more clay. And hydraulic conductivity was an important, knowing where these sandy zones were was very important for purpose of having to dewater this before and during and possibly even after construction of this tunnel. And another project nearby was to characterize this this sort of river crossing here for putting in another bridge. And this is a quite different geology they're interested in here. This is chalk underlying sort of silts and clays. And so in the NMR data, this is showing the pore size distribution of this chalk formation. First thing you'll see is look at the porosity. It's 50%, really high porosity. And it seems like it doesn't really vary that much, the properties of the chalk, but you do see these small variations that that indicate, just finds changes in the pore size geometries at different depths here. And I'm not a geotechnical engineer, but I think these are the properties they were looking for. And anyway, they based on probably some of the geophysics and also the costs, I guess, they decided not to go forward with this project. And I think the costs may have been assessed as being high because of what they found in the geotechnical investigation. Okay, finally, last example here. You can also deploy NMR tools by direct push. So the previous examples were in boreholes. Those were both open borehole logging. And this is an example of a data set with direct push. Let me see, I think I've got an extra slide here. That's okay, so I've got two slides doing the same thing. But anyway, here's the more updated one. So direct push instruments, basically kind of like a small miniature drill rig. If you haven't heard of it, just kind of you can hammer or push down your rods. And this is a typical data set from a geoprobe tool that measures electrical conductivity and hydraulic conductivity. And so this is two sets of data, HPT tool and an NMR tool, both at the same site. And so the NMR tool, you see this really nice high resolution image of the pore size distribution, the total water content, bound and mobile, clay bound, capillary and mobile. So it's just showing a very nice correlation between the high resolution HPT data. It's another measure of hydraulic conductivity that can actually measure over a wider range than the HPT direct push tool. And you're also getting all these information on the water content and porosity. So summarizing the magnetic resonance borehole logging, the value is really you're measuring water content and porosity directly. And you're also getting a continuous look at what's the relative pore size distribution, at least the water-filled pore size. So it's not a direct measurement of hydraulic conductivity, but it's a very good relative measure. And in some types of sediments and formations, I think it's good quantitatively, especially in unconsolidated materials. I think we've got a very good handle on the models there. Can operate in open or PVC cased holes and also by direct push. It's got high resolution. You can log to thousands of meters, just depends on your tool. And I think the most important thing for applying this is you got to make sure you're using a tool that's going to get your sensitive zone out past the drilling disturbance. That's always the biggest issue, especially in groundwater wells where you've got, especially in monitoring wells where you've got a PVC casing and then you've got an annular space around that. Typically in the United States, for a monitoring well, you have to have 2 inches of, a minimum of 2 inches of annular space between the outside of the casing and the drill boring. And that's filled with either some sort of filter pack if it's in a screened interval, or typically grout if it's in a non-screened interval. So if your sensitive zone is inside there, then you're going to be measuring the NMR properties of the grout. And most people don't really care so much about that. They want to know the native formation property. All right, surface NMR. This is actually my favorite. So this is basically still an NMR measurement, but it's completely different in the way that you're trying to obtain the data and the type of instrumentation that's being used. So I alluded to earlier, you don't have permanent magnets here. You have one permanent magnet, it's the Earth. You're using the Earth's magnetic field. So you're doing these measurements in the Earth's field. You lay these typically pretty big loops of wire on the ground. You do your transmitting and detecting. Typically, you have to deal with noise sources, so you put out additional reference loops to measure the noise and cancel it. That's a very important technique. And this is the sort of data that you get. It's not super high resolution like you get with the NMR logging tools, but nonetheless, I think it's pretty good. It's typically better than a time domain system. It's more on the order of a high resolution resistivity in terms of its vertical resolution. So how does it work? Well, I think we've already described this, but basically you're in the Earth's field, so you have to know what the Earth's field is when you're doing this measurement. So you can measure it locally. Typically you don't need to. There's online map, Earth's field map models that are very good that we typically rely on ourselves. And so you have to know the orientation and strength of the magnetic field so that you know what frequency to transmit at. So you transmit on this big loop, and then you turn it off. This causes excitation in the ground of the water, and then you get the spinning of the protons, and then you use the same loop to detect those. So one thing that's different here is that you have to run different current levels through here. So you run through a range of current levels when you're transmitting, because the water that's in the very shallow subsurface is going to give you the biggest response when you use a small current. And the water that's deeper, it's going to give you a bigger contribution when your current is much higher. So this is how we get information on which to image vertically through this process of just using different current amplitudes. So typically we range over 2 orders of magnitude, different current. So for data processing and interpretation, here's your measured data. This looks a lot like the NMR log. It's just basically your time decays here stacked, but this is not on a function of, the y-axis here is not a function of depth at this point. This is basically pulse moment, current pulse moment. So these are the large current excitation currents down here, and these are the small excitation currents here. So what we do is we take this set of data where we know how much current we transmitted, we know the size of the loop, we know the Earth's field and orientation. And so we do a geometric model that relates these measured data to a model of how the Earth would respond at different depths. And then, so it's basically just set up a simple matrix equation, solve it. It's a relatively simple spatial inversion. And the output of that is a set of NMR signals that are now sorted in terms of depth. And they're also scaled with respect to 100% water content. So then the next step, so you can look right here and you can say, all right, well, there's an aquifer there and there's one there and there's not much here, not detecting much water here, but they see two areas with long signals, one here and one there, and a little bit of a break between. So you can do the same sort of multi-exponential fit that we do in the borehole logging to get a relative pore size distribution. That's what you see here, and it's basically the same modeling to estimate bound and mobile water content and permeability from those. So the key difference is here. This relies on an inversion, whereas the borehole logging, it's just wherever the sensor is in depth. Okay, there's some very important limitations for surface NMR. It's really cool because it's really powerful to be able to sit on the top of the Earth and directly detect groundwater, and to even image it and quantify it. But it does have its limitations, and the main limitation historically has been noise. So you've got this big, huge loop out there. You're detecting a really small signal, hundreds of nanovolts, sometimes tens of nanovolts on this big loop. That big loop is really a good detector for all sorts of noise as well, particularly power line, harmonics. So this is an actual example here of measured data. This is not uncommon to see this sort of amount of noise. And this is actual data where we've used this technique where we put these reference coils out towards the noise sources. So we're recording the noise independently as we're recording the NMR data. And then in post-processing, we use adaptive signal processing to cancel the noise out. And it works really well a lot of the time. This is a typical example here where the blue signals before we applied the noise cancellation, the red signals after. And you see this beautiful, clear NMR signal here where before you saw nothing, it was just so noisy. So this is really, that innovation in particular has done more than anything else to make this technique commercially viable, I would say, and a bit viable for use in a lot of areas. So a second limitation or difficulty is if you're in magnetic geology. So in magnetic geology, you have these, the Earth's field is no longer uniform in the subsurface. It's going to have gradients on a large scale, like over the size of your loop, and so you're going to have gradients on the order of the pore size, pore scale gradients. So that causes when you have this effect, it causes the relaxation times to be artificially, or it causes them to be faster than they otherwise would be if it was a non-magnetic. So we do have pulse sequences now, like the CPMG sequence, that can still measure the pore size related time decay, which is really what you want in the presence of magnetic geology. But there still are some situations where the magnetic field gradients are so high that you just have difficulty detecting anything. That's just a limitation. It's a physical limitation of the technique. And lastly, the depth of investigations, and it's another limitation. You basically are limited by about the size of the loop you can put out, and the size of the loop that you can put out is sort of limited by the amount of current and voltage you can apply to it safely and without going to extremes. So you may see references that say 150 meters is the maximum depth of investigation. And you may be able to get 150 meters if you're in a highly resistive geology and you're in a low Earth's field, like you can in South Africa, for example. Low Earth's field, so you can get more current through the loop. But I think the sweet spot for this technique is really like less than 100 meters. And less than 50 is where you can really get high resolution data, usually. So this is an example. This is the same one we used in the introduction here. So this is it's going to show what the actual subsurface looks like here. You have the top 10 meters is silt and clay, and then there's a sharp transition to the sand and gravel alluvial aquifer. Water table here was about 6 meters, so you see you're starting to detect water, but it's in very small pores. And you don't detect all of the water in silt and clay. That's another limitation of surface NMR. It's not able to detect the water that's in the smallest pore sizes. And so you have sand and gravel, and then this limestone formation below, which kind of surprisingly had the highest permeability estimate and quite a bit of mobile water content. Another example here, this is from Nebraska. These are both, this is a groundwater resources modeling project from a few years back. And again, you see the water table in this case was about 5 meters. You have a silt and clay, loamy silt and clay down to about 10 meters. And there's an alluvial aquifer, which is clearly imaged here in the surface NMR. And below that, there's Ogallala sandstone formation, which is kind of a semi-consolidated, still high permeability, but probably not as high as the alluvial aquifer. So one of the other things is you have to have an understanding of like, well, what is the maximum depth at which I can interpret this data? So just looking at this, you wouldn't really know. You may misinterpret and say, well, there's no water below 60 meters, but that's not true. In this case, we just can't really detect or image it below about here. And so, most of the modern software that do these sort of inversions also give you an output like this that says, okay, here's sort of the limit at which you can interpret this data reliably. So it's not like you get like an instant fall off in your sensitivity, but below a certain point, it does drop off quite rapidly. So I wouldn't try to interpret this data below 60 meters for this particular data set. Another nice thing about NMR measurements in general is that they're generally insensitive to the electrical conductivity of the fluid itself, or even the subsurface. So what you're basically doing, they're directly sensitive to the water, the hydrogen, and also the pore size. So that makes it valuable in sort of a lot of saltwater intrusion or anything having to do with ambiguity where you get high electrical conductivity in the subsurface because of the fluid conductivity. So in this case, we had a groundwater investigation here. This is just north of where we are. And the study area is here, this little island in this low spot between this residential zone and this one here. So in this particular area, you see this river coming in here. This is a important salmon and steelhead river, the Stillaguamish River. And so it discharges into Puget Sound here. And the Fish and Wildlife Department they owned this piece of property. They bought it because they wanted to turn it back into, historically it's a marshland. They wanted it, and it got converted over to partial use in farming. They bought it, they wanted to flood it. They wanted to knock down these levees and flood it to create habitat for juvenile salmon. So that all sounded great until these people started thinking, hey, but what if they flood this with salt water? We've got our groundwater wells here. This is going to cause a problem. It's going to intrude in our, we're start getting salt water in our wells and in our drinking water. So you had lawsuits and everything else, which is kind of typical. But anyway, so we did geophysical surveys here, and there were, we did a number of surface NMR and did some direct push NMR in these two areas here. And this sort of data that we came up with from these studies. This is a direct push NMR log from that site over on the east. And we also did direct push electrical conductivity. And you see that the electrical conductivity here increases, and then you get to about 2 ohm meters, then it's just straight. So there's a transition here at about 5 meters between more fresh water up here and much more brackish water down here. So the electrical conductivity was really not relating, at least below 5 meters, was not really telling us anything about the aquifer structure or the aquatards. It just seems kind of random and very high in general. The NMR data clearly just shows where these aquifer units are, where the breaks are, and in particular down here at 20 meters, there's this really hard clay that comes in. And that's going to have we found this was consistent across the island there, wherever we've done measurements. So that was kind of an important feature that wasn't known. And a couple of surface NMR measurements here. They also are able to define where these aquifer units are and where the silts are. So this is sand and gravel. There's silt. These were in the same spot. This is the NMR, direct push NMR logging. This is one surface NMR, and this is one of these CPMG sequences that is less susceptible to the magnetic effects. And these sediments were fairly magnetic because they derived from volcanic outwash from the Cascades here. This is a 2D, on the top there's finally a 2D resistivity line across a segment there, and then a 2D NMR in the same area. And because of the salinity of the water, groundwater, there really isn't any contrast at all in the 2D resistivity survey at this site, where the NMR 2D survey shows some interesting breaks, especially in the lower aquifer. You see the upper and lower aquifer units here, but the lower one seems less continuous, which was interesting. All right, so I'm almost done. There's a few other kind of niche type of NMR measurements and techniques I'll just go through quickly here. One is a man-portable, a person-portable NMR logging tool. So this is basically the whole thing. You've got a little toolbox-sized transmitter and a probe, and so you can walk around with this. A person can walk around with this. And here's some data that was acquired in Australia using this tool. This is kind of a very rare type of peat lake that is in Western Australia. and it's been stressed because of reduced rainfall, and so it's got a lot of unique features and qualities, and it's under a lot of study by environmental scientists. So they believe that paleo dunes in subsurface are key control on the groundwater here and the lake itself. So their interest in getting some subsurface data out here. It's obviously very difficult to access, certainly not by a sort of a ground vehicle. So they use this tool where you can walk out there, and had some existing monitoring wells that were installed by direct push NMR, and this is one of the data sets they got out here somewhere at one of these locations. And so there's very clearly, there's one of these paleo sand channels right here. And just above it is a particularly low permeability feature with water in small pores. So this is data is very useful for this type of project, and the ability to just go in and hike in somewhere with the equipment it's kind of it's unique. It's got value of its own, just to be able to go in and do small scale NMR measurements of soil or subsurface sediments. This is an example here, Crested Butte, Colorado, where scientists were trying to get a handle on, get some information on subsurface water content in the top couple of meters on the slopes of this valley, just over time, monitoring, basically long-term monitoring over different seasonal cycles. Snow melt, saturation, and drying out in the summer. So this is one of these tools here. There's the logging tool doing a measurement in one of these shallow wells that were installed. Here's a couple examples of data from that study. This is early in the summer, June 2017. So the ground is probably at its highest saturation at this time of year because the snow has just kind of, the runoff period from the snow melt is just kind of in the later stage where most of the water is now in the ground and it's moving down the slope towards the river and lower part of the valley. So you see this site here, that's the basic water content profile at that location and here in the top meter and a half. And then the same locations later in the summer, probably close to the driest part of the year. You see that there's been a large change in the water content, soil water content, and both vertically and along that hillside. Finally, this isn't maybe geophysics per se, but this, NMR can be used on core samples as well, and it is to determine the same sort of properties that you would try to determine with a geophysical measurement. So in this case, you have it's still doing an NMR measurement of the same type, but in this case, you got a different type of magnet array. Typically, the magnets are surrounding the sample, and you put the sample inside the device to do the measurement. So you get the same basic data reduction and processing and interpretation. It's just you're operating with samples instead of putting something in or on the ground to do a measurement. All right, so thank you for this opportunity. In summary, I would say that the unique value of magnetic resonance is you directly detect water. And that's unique. If you're interested in water and the hydrogeologic properties, you get very direct measurements that are directly related to those parameters of interest. Now, surface NMR, it's non-invasive. The key value of surface NMR is you don't have to drill a well. That's what it comes down to. And it still directly detects water. It does have its limitations, but I mean, that's a large value. When you can use it successfully, it's very cool. And borehole NMR, the key thing here is to make sure that your sensitive zone is actually out in the native formation and you're not sensing in the disturbed zone of the drilling. All right, well, we've had quite a bit of funding for this research that we've been involved with over the past 10, 15 years. So I need to acknowledge that from the Department of Energy, and have a lot of great cooperators who have been involved with us when we've developed these tools and applied them in research environments. All right, I think I'm done.
Perfect, Dave. Thank you very much. This was a great presentation and great overview of an NMR capabilities and case studies. I think something happened to your video feed because I could see it's disappeared from the stream, but your presentation went through perfectly and your voice went through perfectly. I don't know if you want to try to switch your camera on and off under MS Teams. Maybe that will.
Okay,
okay, that's perfect.
I just tried to cycle.
I'm just
okay,
gonna.
All right.
That's perfect. You're back. Thank you so much. We have a few questions from the audience. There's actually several questions from Ray Durham, who's asking, what is the length of the interval measured for various shells for stationary and continuous measure? How is signal to noise defined?
Okay, so for, I assume this is for logging tools.
Yep.
Let's see. And so the length, I assume that's talking about the vertical extent of the sensitive zone. Well, I can just sort of answer here about the vertical extent of the sensitive zone is determined by basically the size of the induction coil that you use for transmitting and detecting. So typically a half a meter or a quarter of a meter is that length there. The extent that can be changed. You know, it's a design parameter that can be changed, and different tools have different trade-offs that go along with that. As far as these radius of investigation, this is actually to scale for a particular size of tool. So I think this one is for a 3.5. This rendering was done from a 3.5 inch diameter logging tool, and these four range from 10.5 inches diameter here to about 15 inches there. And the signal to noise ratio does improve as you get closer. So this shell here is going to have typically twice the signal to noise ratio as the outermost shell. And the reason for that is mainly because this shell is much closer to the detector. So you've got a detection coil, and it's just going to be more sensitive to something that's here than something that's out there. So the trade-off is always you want to have high signal to noise so you can have lower variance in your data and also faster logging speed. But the trade-off is a lot of the time you may end up in this unknown disturbed zone or in some part of it. So it's useful to have multiple shells. It's not necessary, but it's useful.
That's perfect. Ray is also asking, what is the order of magnitude cost of an NMR system for surface surveying and for a person portable NMR?
Okay, for surface NMR, I can tell you what our equipment we sell it for. We sell two types of surface NMR system, two products. One is has a depth of investigation of about 50 to 80 meters, and that sells for about 100,000. And then our full powered one, which has a deep, that sells for about 160,000.
Is that US dollars?
Yes, US dollars.
Okay, perfect.
And the person portable one is again about $80,000.
Okay, perfect. Jeff Campbell is asking, what is the range of radial penetration distances for the borehole tool?
Good question. So every tool has a different zone, basically. So the tools that we develop and manufacture It depends first and foremost on the diameter of the tool. So we have tools like that Person portable one. It has 1 3/4 inch diameter, the tool itself, and it sees at in radial shells or diameters of 5 and 6 inches. And we have another version of that tool that sees at 9 and 10 inches. This intermediate size tool here, this is a 60 millimeter. I'll try to do what I can in metric here. 60 millimeters diameter, and its zones of investigation are 9 and 11 inch diameters. So it's out here. The bigger the tool, the bigger your zones of investigation, basically. So you always want to run the biggest tool that you can deploy in whatever borehole or well, because it's going to see out farther. If you got a bigger boring, you got to use a bigger tool. I mean, bigger in terms of a larger diameter. So the very biggest tool that we use has 5 1/4 inch diameter for the tool, and the largest sensitive zone has a diameter of 21 inches. And so that's useful for large diameter production wells, of which in the United States, it's not uncommon in the Western United States for production wells to be drilled. A pilot hole would be 17 to 20 inches. So all around the world, people have different types of drilling and well construction. So you just have to, this is the key thing. Just make sure your tool, whatever you're using, it's going to be out there in the native formation and keep it centralized in the borehole.
We have a question from Kimo. For surface NMR, what is the typical size of the loop? Also, what is the maximum aerial extent that can be achieved with this kind of survey? I'm trying to understand if this is not labor intensive, if much ground needs to be covered.
So the typical loops, there is not really a typical loop size. You want to use a loop that is a little bit bigger than the maximum depth that you're interested in investigating. So if your investigation is you're only interested in the top 10 meters, you can use a loop that's 10 or 20 meters. And it's actually better to use a loop that's smaller for that type of investigation because you get better resolution and typically better signal to noise and better noise cancellation. Now, if you need to investigate to a depth of 100 meters, you should be using the biggest loop that you can put together. 150 meters is what I would use. So the thing is that this is all based on the magnetic fields that are generated from this surface loop. And if you take a circle and you look at the magnetic fields generated by a current loop of that size, they vary quite a bit within that first radius or even down to about 1 diameter. You get good variation, and that's what gives you your ability to resolve in depth. But the sensitivity overall really plummets off a cliff once you get down below about 1 coil diameter. That's why you need to use a big loop, and the loop should be at least as big as your depth of investigation that you're trying to achieve. Now, there was another question about aerial extent. Maybe could you clarify that question a little?
I'm going to try to. Just 1 second. I'm trying to get back to the actual question. Okay, while I'm trying to clarify that, I'm going to move on to the next question. Terry Odges is asking, would surface or borehole NMR be useful in the exploration phase of fracking applications?
Well, surface NMR is only going to be useful to, like 100 meters depth. So if you're fracking at greater depths than that, then surface NMR is not going to be probably that useful. Certainly if you're down like thousands of meters, surface NMR can't get anywhere close to that.
Okay, the next question is from Brad Pitts. Is there any potential for using repetitive measurements to monitor sinkhole formation?
With surface NMR, I think.
Yes.
Probably.
Yeah.
If it's filled with water. So the thing is, if it's a sinkhole that is filled with air, you're not going to detect it. If it's a sinkhole that is filled with water, I mean, that's what you're detecting. You're imaging the water, not the rock or the absence of rock. It's the absence or presence of water. That's an interesting application. I think I mean, it certainly could be useful if you got a sinkhole that's developing and it's filling with water, bulk water. That would be very easy to detect and identify, because bulk water that's in a big void like that is going to have a very long relaxation time compared to any water that's in any sort of sediment.
Perfect. Ray's asking, the results in the 90s showed that the Meg gradients above 100 nanoteslas under the loop equals poor data. Question, what is your experience?
Let's say I'm gonna have to try to figure out what 100 nanoteslas. Let's say you got 40. I'm trying to figure out how much of a shift in the resonant frequency it is. Let's see, 42.1 times. That's only a 4 degree. So you basically, what that does is it causes a spread of your NMR frequency by about 4 hertz, that much of a gradient. And so I would say that these days, that's not that hard to deal with. So the reason is, there's a couple of reasons. One is back in the 90s, the instrumentation that were available at that time, they had a very long dead time, and there were no sort of spin echo or advanced pulse sequences to deal with the magnetic dephasing is what was happening. So I think back in those days, that would be probably a very difficult detection scenario. More modern instrumentation has a much shorter dead time, so you can, basically what happens when you have a magnetic field gradient is you get this rapid dephasing of the signal. So it you have to be able to detect earlier in the, let me see if I can find a slide and demonstrate. You have to be able to detect earlier. So actually the way the pulse sequence goes, you do your transmit pulse here, and then there's a dead time between transmitting and receiving. And so if you're in a very high gradient, this signal, instead of being nice and long like this, will be super short. And so that's what was preventing detection, and still can if you have a certain degree of magnetic field variation. But you can also do refocusing pulses like this, which cause the signal to sustain and come back and refocus at much later periods in time. So I don't think it's nearly as limited as it used to be with magnetic geology, but there is a limit. You know, you get to a certain point where the magnetic field gradients at the pore scale and at the loop scale just get so large that you can't detect anything, or it's very difficult.
Perfect. The next question from Susan Webb. How long does a surface measurement take? How long does it cost per station? And would it be possible to combine measurements with CSMT?
It's a good idea to combine measurements with some sort of electrical resistivity profile. That's because the inversion to get unless you're in a known very resistive subsurface, the inversion is going to depend on knowing what the resistivity profile is, at least having a decent model for it. So the NMR inversion benefits from a resistivity profile. Now, second, how long does a measurement take? It takes a while just to set it up. You know, depending on the size, if you've got a big full power system like this, you got to get it out of your truck, you got to lay your loops out. It can take a half an hour or 40 minutes just to get it set up and then tune in the loop. The amount of time you have to is required for data acquisition depends entirely on the signal to noise. So we've done plenty of times in low noise environments, or where we could cancel noise effectively. We had perfectly usable data within 10 or 20 minutes. We could just stop right there. sometimes you have to sit there and average for a long time. Sometimes, half a day is not uncommon, 3 hours. So when I advise people who are interested in using it on a project, I would say, given the effort that it takes to set up in the field and the time associated with that you should probably, without knowing anything else, I would say figure on doing 1 or 2 sites a day until you get quite better knowledge and proficiency with it. And so what's the cost? The cost would be basically, what is the labor? It's basically a 1-person job, except you do need 2 people typically to pick this stuff up. So you want probably your best geophysicist, to somebody who's really motivated and interested, to be the lead on this sort of thing. It's a bit trickier than it is, a time domain survey. There's more things that go into, making sure you get these noise loops put out properly. This can have a big impact on the data quality and the success of the survey. So the cost will come down to your labor cost and whether you're buying or renting or already own this equipment.
And that's perfect. Another question is also from Susan Webb. Is the input field, or is it analogous to passive seismic? And could you monitor changes in water level?
So you can monitor changes in water level to the extent that you can resolve that. With surface NMR, this is a typical resolution. Your resolution is better at this close to the surface, and then it tails off as you get farther away. I would say it's not the best application, monitoring water levels, unless you have really big changes, like seasonal changes that are causing your water table to drop by 10 meters or more. So the first part of the question I've forgotten.
Is there an input field, or is it analogous to passive seismics?
I'm not sure. It's a you are transmitting. It's active. So
okay, there is an input field.
This equipment is generating really huge current pulses, like 600 amp pulses on this loop. You might be able to see there's this big loop out there, the yellow. So there's a lot of power generated, and you got 4,000 volts on the terminals of this loop when you're transmitting at maximum power. 4,000 volts and 600 amps pulses going through here. Perfect.
We have another question from Anonymous. What is the depth and pressure limitations on the borehole tools?
Well, it depends who's made the tool and what the purpose is. So, oil field NMR tools are, they're designed to go 20,000 PSI, 6 miles deep and, 150 degrees Celsius. Our tools are the ones that we produce. They range from the dart, which is really only 100 meters, so it's got a very thin wall. And the deepest tools, the tools with the highest pressure and depth rating that we're involved with, 2,000 meters in terms of pressure and 70 degrees C for temperature. And not all of the tools that we make are even that high. They're designed for groundwater applications. Ours are not designed for oil and gas.
Perfect. We have another question from Ray Durheim. What sort of station spacing would you use when profiling, when searching for water-bearing faults or dike contact?
I wouldn't know where to start. I would have to know more about the site or the sites and what sort of scale of investigation it is. I will say that if you just have a single loop, you really are only sensitive to basically what's right underneath that loop. So this loop here is not going to be sensitive it's going to have little sensitivity to groundwater that's underneath this spot. So it is very highly localized. So if you've got a fracture running through here, and you do a measurement here, and then you skip that, and you do a measurement here, you're likely to miss it with surface NMR.
Perfect. We have a clarification regarding the previous question that Susan Webb was asking regarding the regarding an input field. The question was related to for a small portable system, is there an input field or is it similar to passive seismic?
I don't, my understanding passive seismic is just listening, and it's from just other sources of seismic activity are the source. So I guess I still don't quite understand the question, but we definitely create the signal with NMR. NMR is not passive. You generate a magnetic field that causes an alternating magnetic field that causes this precession and this rotation of the hydrogen, and then that's what you detect. You detect that hydrogen atom rotation and the magnetic field that it generates.
Perfect. We have another question from Jeff Campbell. I'm gonna read this out now. Does the surface method use an on-site generator or bank of batteries to power large currents required? Question from Jeff Campbell.
Typically a couple of batteries. There's a group in Denmark who've developed a surface NMR system that runs on a generator, but that's the only one I know of, is that group in Denmark. So all of our equipment runs from a couple of car batteries. You can see them here. A couple of deep cycle batteries are good. And the way the current pulses are generated, it's not directly from the batteries, at least with our equipment. The batteries charge a DC converter, and you see this box here? That has 12 very large capacitors in it. So basically this part of the system takes the 24 volts from the battery and charges it up, charges these capacitors to a varying amount of voltage so that we can control different amounts of current going through the loop. And so the current pulse comes straight from these capacitors.
Perfect. Dave, I'm gonna just double check that we've covered as much as we could in terms of questions. If I did leave anyone out, I do apologize up front. There was quite a lot of questions was coming from the floor. Dave, on that note, if anybody has any questions regarding the presentation, could we pass on your contact details so they can approach you and chat to you directly?
Yes, absolutely. Perfect.
Dave, once again, a huge thanks for taking the time to take us through it. If you can, please join us for a catch up on a Google Meets link that I've posted in the chat window. I'll also send it to you via Skype. If you ever find yourself in South Africa, please give us a shout. We'll keen to host you for dinner if you ever have the opportunity to come through.
Well, I plan to. Thank you. I appreciate that. As soon as the circumstances allow.
Yeah, absolutely. We live in the challenging times. Once again, Dave, a huge thanks for presenting to the SAGA community, and have an awesome day.
Okay, thanks.